Hey everyone, and welcome to the first of hopefully many topics going through Calculus 2. So this first topic is going to be on the limit definition of the derivative. And since this is the first topic, we should probably talk about what calculus even is. Calculus is commonly called the study of change. But to understand what that means, we should probably discuss slope, which is hopefully a concept you guys know by now. Introduced in the first couple of algebra classes you might take, slope is commonly called the rate of change. It's the rise over the run. If you go across this amount, you go up this amount. So let's kind of introduce what I mean by that by talking about secant lines. Secant lines. So to introduce secant lines, we're going to introduce some kind of function and a graph. So let's draw this graph, and let's call it f of x, and this will be x. And it'll look something like this. Okay? And now we're just going to choose 2 points. Completely random. Here and let's say here. The secant line is the line that goes through 2 points on this function. So it'll look something like that. Goes on forever in either direction. So this is the secant line. A secant line has a slope, of course, but how do we calculate that? Well, let's look. Slope is commonly calculated as rise over run. So I'm going to draw a little right triangle here to calculate the rise and the run. And just to get used to some notation you might see in calculus, I'm going to call this the delta y and this the delta x. All this means is the change in y values, and this is the change in x values. So if this is x2 and this is x1, well, to calculate the slope is pretty easy. Let's say if the slope is called m, then this is just going to be f of x2 minus f of x1 over x2 minus x1. This is the exact same as writing dy over dx, because the change in y values is f of x2 and minus f of x1, and naturally the change in x values is x2 minus x1. So hopefully that's pretty straightforward, calculating a secant line. But in calculus, we're going to be more interested in what we call tangent lines. So a tangent line actually looks, let's say a tangent line at x1 looks something like this. There we go. So the tangent line, as you can see, is going to be the line that barely touches 1 point on the graph. While a secant line clearly goes through 2 points, a tangent line is designed to just barely touch the graph and go off. So in physics, you might understand this as the velocity of a position function. If we imagine this graph to be the position of some car driving, then the tangent line at any point is the velocity it's going. So, how might we even calculate this tangent line? I mean, it seems pretty arbitrary, but the secant line can help us, and our friend limits. So hopefully you know a little bit about limits right now, but they're going to come in handy when calculating the derivative, which is also called the tangent line. So let's just see what happens when we bring x2 closer and closer to x1. So if x2 was here, 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 let's see the lines that it creates. Boom. So you see, as x2 approaches x1, the secant line approaches the tangent line. So this idea of something approaching something else is actually going to help us formalize our idea of the tangent line or the derivative. So let's just formalize our argument a little bit here. Instead of using x2 and x1, we're going to use x and x plus some delta x. So let's call this x. And let's call another point x plus delta x, which means our delta x is quite literally delta x, and our delta y is going to be f of x plus delta x minus f of x. So what we can say is, if we want to now calculate the tangent line at x, we can say the slope is going to be f of x plus delta x minus f of x. This is our rise, all over our run, which is delta x. Now this is pretty good, but if delta x is large, as in like 2 or 3, well then you're going to see large discrepancies. So let's say if delta x meant the second value is all the way over here, this secant line is nowhere close to the tangent line. So we need a limit as delta x approaches 0. And because of this, now we literally have the derivative. This is equal to the derivative, or the tangent line, at x. So all the derivative is a secant line coming towards a tangent line at some function. In physics, we may understand this as the velocity, or if you're looking at a velocity graph, the derivative is the acceleration. So let's try some examples with this, because right now it's kind of in a more theoretical idea. So let's try some examples to wrap our head around this. So let's try a function. Let's call it f of x equals ax plus b. This is just going to be a regular line that you all know. And it looks something like this. Okay? Luckily, lines are pretty easy because we actually know the derivative already. The derivative is just the slope of the line. I mean, that's the definition, right? And the line has a constant slope. In fact, it's right here. It's a. So we're going to say the derivative, which we also call f prime of x, equals a. Now we know this is true, but let's see if we can find the same value using our limit definition of the derivative. So let's rewrite it. Limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. So what is x plus delta x? Well, we just plug it into here and we get ax plus a delta x plus b. Then subtract f of x, which is going to subtract ax and going to subtract b. All of this over delta x. So we see we have an ax cancel, we have a b cancel, and all we're left is a times delta x. Delta x over delta x. Now clearly these two cancel, and all we're left is with the limit as delta x approaches 0 of a. And since delta x is nowhere in this final equation, the limit doesn't matter. And so we have proven that f prime of x equals a. So this is the power of the limit definition of the derivative, because your functions are not going to be as common as a line, right? You might have a trig function, you might have an exponential function. And in these cases, we're going to need the limit definition of the derivative to prove it. But once we do it once, we can usually formulate rules that help us never do it again, because the process is a little bit lengthy and a little bit of annoying. So we're just going to do one more example to show another interesting idea and something that's not as obvious. So let's take f of x equals x squared. this is no longer a line, and it's actually going to have a changing slope. So you can look at f of x squared yourself, and you'll see the derivative, the tangent line, or the slope, is not the same at every point. So we expect that our answer, f prime of x, is going to rely on x in some way. It's not going to just be some constant. So let's try it out. So we're going to get f of x plus delta x minus f of x over delta x. So what's x plus delta x squared? It's x squared plus 2x delta x plus delta x squared. And then minus f of x, which is just x squared. All of this over delta x. So now x squareds cancel. And what we can do is we can factor out a delta x and cancel it out with the denominator, and you get something that looks like this. The limit as delta x approaches 0 of 2x plus delta x. Now, this is actually super easy to do. We just evaluate at delta x, because now we have no problem with dividing by 0. We plug in 0, and we just get f prime of x equals 2x. And just like that, we prove something not so obvious about the derivative of f of x equals x squared. And in fact, this will lead us to something I won't prove right now, but you can try on your own, is the power rule. If f of x equals x to the n, so in this case n was 2, then f prime of x equals n times x to the n minus 1. So you can see if you plug in n equals 2, which is what we had for f of x equals x squared, you get 2 times x to the 2 minus 1, which is 1, giving us 2x. If you had x cubed, or n equals 3, you get 3 times x squared. So this is kind of the most basic rule you'll learn when first learning derivatives, and you're going to learn way more to help you with a bunch of different derivatives later throughout Calculus 2. And hopefully in another lesson we can introduce some basic properties of derivatives that will get you much further than what you know right now. Thank you.